Hello, this is an answer sheet for the first worksheet on transformations. I'm quickly going to go over the first page because we have already done it. For the most part in high school, we deal with sets of ordered pairs, x and y. They can be defined as either a relation, any set of ordered pairs, in which you can draw any closed shape, or a function, any set of ordered pairs in which each member of the domain corresponds to a unique element in the range. The shortcut is the VLT, and here's a picture of a member of the cubic family. The notation is we replace y with f of x or g of x or whatever. Here's an example. There's a function. I know it's a function. I'm using function notation. It's also a quadratic. One of the powers of function notation is I'm able to do these questions quickly, at least outline them. I want to find the value of the function called f when we let x be 3. I plug 3 into here, I will get 32. If I plug -6 into f, using my calculator, I'll get 113. If I plug something like this into f, I set it up like this. This is a difference of squares. That squared, that times that, doubled, that squared. Multiply by 3, add 5, I get this. This is something we've done. This is just a quick review. Hopefully you had no trouble with that. On the back side, families. Again, we've been over this. If we use the exponents, if the degree of the equation is 1, it must be a member of the linear family. And we have two types of equations. Y equals mx plus b, 0 equals ax plus by plus c. Rather useless. There's an example. If the degree is 2, then it's a quadratic. And we have y equals ax squared plus bx plus c, or vertex form, or we could even have factored form, in which we get a parabola opening up or down. If the degree is 3, it's cubic. Now, instead of being a 3, it could have been a 5, or it could have been a 7. These have names, but it's just simply easier to call them cubics. They have the same characteristics. Here's the equation of a cubic. Ax cubed plus bx squared plus cx plus d. This is the general shape of a cubic. This is the general shape of a quintic. You don't have to know that. Now, if the exponent is not 3, 5, 7, 9, but if it's 4, 6, 8, it has the same characteristics as a quadratic, so we just call them parabolics. You don't have to know the name of these. Here's part of an equation of a quartic. ax4 plus bx cubed plus cx squared plus dx plus e. Here is a diagram of a x to the 4th. Here's a diagram of x to the 6th, parabola opening up, parabola type thing opening down. Then we can ignore the exponents and just go to the name, radical. We have seen this already. Or I could have listed this as x to the 1/3. We've already covered that. Here's the equation of this one, y equals x squared. There is nothing on the other side. We cannot take the square root of negatives. This one, y equals the cube root of x. We have this tail as well as that tail, because we can take the cube root. We have rational functions. A group of terms containing an x divided by a group of terms containing an x. We get this feature, which is an asymptote. We have something like this. The last one on this particular page, no exponent, is absolute value. Whatever goes in here, a positive must come out. Here's an example. This would be y minus 2, and then this would be -3. Again, we've been over that. This takes us to the first page we really want to talk about, the next one. Transformations. Transformations can happen to any of the families we just talked about. The first one we're going to do is horizontal transformations. We'll begin by just starting with one of our basic ones, a parabola. I can take that parabola without changing its shape. I can shift it over. this guy would have an equation y equals x squared. This one would be y equals x minus 5 squared. Although we're moving at 5 to the right, in a bracket, it looks the opposite. What makes that bracket equal to 0? 5. So that's it. I can move the parabola the other way. -6. This one will be y equals x plus 6 squared. This is shifted left or right. That's what horizontal transformations do. In terms of domain and range, the domain will change. The range, there is no change. And we qualify that by saying usually, depending on the family of the function we're dealing with. Instead of having a horizontal transformation, we can have a vertical transformation. And this time I'm going to draw absolute values. Y equals the absolute value of x. Vertical means up or down, so although it doesn't change its shape, this guy could move this way. The equation will now be, this is outside the bracket, so it is exactly what you would expect. Everything got moved up 1. I could have it down here at -4. In this case, it'll be y equals the absolute value of x minus 4. Again, it's outside, do what it says. Vertical shifts move up or down. The domain, no change. If you look at these, the vertex is there, the vertex is there, the vertex is there. That has not changed. But the range will change. Let's come down here. I'm going to do horizontal change. Here's a circle. It's not a function, but big deal. There's the center of the circle. -1, 1, 2. This has an equation of f of x. It's going to be moved over 1, 2, 3. And it's getting moved to the right, so it'll be -3. That would be the equation. This one, if I move it up to here, everything gets moved up the same amount. There was 1, we'll call that 2. This guy is f of x. This guy will be f of x and simply moved up 1. That got moved up, that got moved up, that got moved up. That ends this particular section. I'll do the next pages on another video.